first of all, thank the organizers for the invitation. And in this particular talk, we are going to share some of our recent results on twist 2D magnets and also some puzzles because we don't understand everything yet. So the twisted magnets we are looking at is twisted double bilayer chrome trioxide. So it is a bilayer chrome trioxide on top of another bilayer chrome trioxide with a small twist angle. So let me start by giving some basics about chrome trioxide, this magnet material. So it's a van der Waals material, so that we can peel with. So then within each layer, we will have this kind of chromium iodide octahedral cage. And then this cage arranged into a honeycomb structure. So when we stack such layers into thicker ones or bulk ones, there are actually two stable structures. For the bulk chrome trioxide, below a critical temperature of 200 Kelvin, the stacking takes this rhombohedral stacking. And then for the few layer cases, it's been established in the community that the stacking takes these monoclinic ones. Magnetism-wise, below some critical temperature, within the layer, it always favors the so-called interlayer ferromagnetic coupling, has a easy access anisotropy along the outer plane direction. But then more interestingly is about the interlayer magnetic interactions. It actually depends on this geometrical stacking. So if it is this kind of rhombohedral stacking, it will take the interlayer ferromagnetic coupling. If it's monoclinic, it will take the anti-ferromagnetic type. So then let's just take a look at a few layer cases to make a few remarks. So when people apply the magnetic field, since now we have this kind of a layered anti-ferromagnetic order, it will undergo these spin flip transitions. There's a first spin flip transition field around 0.6 Tesla. So this corresponds to the outermost layer to be flipped along the field direction. And then at a higher field, there's another spin flip transition that is about 1.4 Tesla. This corresponds to the inner layers here, flip along the field direction. So that's for the few layer cases. So then let me just give a brief wrap up of what's happening in chrome trioxide if they're natural. So first of all, this is a easy access collinear spin magnets, either layered antiferro or layered ferro. They are collinear. Okay. Second, for the even layer cases, they have compensated magnetization. So meaning that for 2-layer or 4-layer, we have 0 magnetizations. Okay. And then third, which is most important for the so-called Moiré magnetism, is that the interlayer magnetic interaction depends on the interlayer structure stacking geometry, being ferromagnetic for rhombohedral and being anti-ferromagnetic for monoclinic. So then based on this kind of knowledge, people may wonder if we take 2 of these layers and then give them a twist to generate this kind of a Moiré superlattice, we will certainly have different stackings within the Moiré supercell. So here we are highlighting a few. So for example, we will have this kind of overlay geometry where the honeycomb perfectly sit on top of each other. And through the calculation by Deschamps' group, that tells us that this will have negligibly small interlayer coupling. And of course, we will have this kind of rhombohedral stacking when one sits in the center of the other. So for this kind of rhombohedral, we learned from the previous knowledge that they will have ferromagnetic type of interlayer interaction. And then in between, we will also have this kind of monoclinic stacking. For this one, we will have anti-ferro interlayer interaction. So then when we look within the Moiré supercell, we will see the interlayer interaction switches from 0 to ferro to anti-ferro. It's modulating. And then if you have such a superlattice, then your spin Hamiltonian is modulating at the Moiré wavelengths. So theoretically, it's been a question to the community, what kind of magnetic ground state it can be if we have such a spin Hamiltonian. So theoretical predictions including we can have interesting non-collinear spin state, and examples also include a skyrmion state and also chiral magnetic phases. And then magnetic excitation-wise, there are also predictions about interesting ones, such as one-dimensional magnons or topological magnons. So those predictions really motivate experimentalists to look into the system and see what can happen there. Okay, so our work sort of start by saying we cannot look at the magnon at the beginning. Let's look at the magnetic ground state first. So this is about this talk. Okay. So we choose our system to be twisted double bilayer chrome trioxide, as illustrated here. It's a bilayer on top of another bilayer with a small twist angle of alpha. So then when we look at this 4-layer structure, if we consider the interlayer interactions, we will have uniform anti-ferromagnetic coupling between the layers within the bilayer. So then, which is between the first and second layer and between the third and fourth layer. But between the third and second and third layer, that's where the interface of the two bilayers, we will have the Moiré superlattice. And that's where we will have the modulated magnetic interactions. Okay. So then the reason for us to choose bilayer was twofold, perhaps. So first of all is that we have been measuring Raman spectroscopy of natural chrome trioxide for a while. So then when we're trying to look at the monolayer versus bilayer, we can see that the bilayer's phonon line width is nearly only a third of the monolayer. We don't understand why monolayer has a wider line width, but we do think perhaps there are more complexity in the monolayer. So that's the reason we choose bilayer to start with, because it fits into our intuition of a high quality material more. Okay. The second one is that we start with a bilayer, which is actually zero magnetization. So then when we try to add them together on top of each other, if we do homogeneous stacking, either it's rhomohedral or it's monoclinic, it will give us zero magnetization because we have two antiferromagnet on top of each other with a homogeneous stacking. Okay, but then if we put rhomohedral and monoclinic next to each other, as if in the Moiré superlattice, we will have conflicts in two layers. So then the question is really how the system would arrange given the conflicts of the two layers if they were to take their naturally favored structure. Okay. And I would like to say that there are parallel works in the community, so including Professor Xiaodong Xu's group doing 3-layer by 3-layer, and Professor Qinfei Mak and Jie Sang's group doing monolayer plus monolayer, and Professor Yong Chen's group doing bilayer plus bilayer. Okay. So then to make the sample, we really just take the community's method, the tear and stack. Because chrome trioxide is kind of air sensitive, we just do everything in the glove box. We find a large flake of bilayer, we tear them into two parts, we stack on top of each other, and then we encapsulate within the hexagonal boron nitride. Then we take out for the optical measurements. Okay. So then before we do the actual optical examination of the magnetic properties, we first would like to check the structural property because we are dealing with Moiré superlattice. We want to sort of like get us convinced that there are actually Moiré superlattice in the system. And we also want to see what's the quality of the Moiré superlattice. So then we collaborated with Professor Houghton's group at Michigan to do this electron diffraction measurement and also the transmission electron microscopy measurement. So let's see the electron diffraction measurement first. So here we are showing the scattering peaks. So in the 3-3-0-0 order. So where you can see there are two brighter peaks or darker peaks in the plot. The two darker peaks on the outside, they are the nuclear peaks from individual bilayers. But in addition to that, you can see also two peaks sitting in the middle of the nuclear peaks. These two peaks are the Moiré superlattice peaks. So interesting in this system, they are actually a second order Moiré superlattice peak. So then when they convert into the real space that you will see here, the wavelengths they are seeing are actually 1/√3 of the actual Moiré superlattice. As to the reason why it's a second order Moiré superlattice showing up, it still remains to be a mystery to us. We don't quite understand why it's structurally it behaves like this. Okay. So this side, as we were saying, it's a reconstructed dark field transmission electron microscopy measurement. And the field of view is about 200 nanometer times 100 nanometer, which is slightly smaller than our optical diffraction limit. But within this range, if you look at the fourth image here, it's actually quite uniform Moiré superlattices here, which is consistent with the ability of seeing the Moiré superlattice peak in the diffraction measurement. Okay. So then we do our optical measurements. The optical measurement has been introduced by Professor Xiaodong Xu in the previous talk, which is magnetic circular dichroism that measures the reflectivity difference between the left and the right-handed circular polarized light. And typically we consider this signal is proportional to the magnetization of the system. But recall that we were dealing with a bilayer on top of a bilayer. If we do homogeneous stacking, we wouldn't expect any magnetization in such a system. So then we take a look at this signal in the twisted sample at 1.1 degree. So what we see here is that instead of having zero magnetization, we actually have finite magnetization in this compound at zero field. Because of that, we see this hysteresis loop. In addition to that, if we compare to bilayer and four layer, it shows this kind of beautiful plateau behavior, meaning that outside of the spin flip transition, the spin state stayed constant over this plateau regime. While when we look at this twisted sample, we clearly see such a slope here, meaning that the spin state is gradually changing as we cranking up the field. And in addition, we also see a spin flip transition that is at a similar field strength to the first one, which is 0.6 to 0.7 Tesla. So that is our experimental data here. So then from this experimental data, we want to say that, first of all, in this twisted 1.1 degree sample, we actually had a magnetization by twisting to zero magnetization material, which is kind of surprising. Second, this material initially was a collinear easy access magnet that shows plateau behavior between the critical fields. While here, we seemingly made the material a little bit more softer that our state gradually changing as we gradually change in the magnetic field. So that's the two major contrasts to the natural field layers. Okay, so then my student Xiangpeng, who actually proposed to fit the data, because we don't know the microscopic picture to start with, but then we can always fit the data to extract some meaningful parameters and then trace those meaningful parameters, temperature dependence or field dependence later on. Okay, so the fit is done in such a way that we consider in the twisted chrome triodide sample, there are two contributions to the signal. One is still the spin flip transition that accounts for this kind of steep jump in the data. Another is a spin flop process that accounts for this kind of gradual changes in the data. So then it's a linear add up of the two contributions to reproduce the raw data. So here, it's a raw data split into the two parts that we were saying. The first part is a collinear spin contribution, okay? And the second part is a spin flop process. And for the spin flop process, we attribute to the non-collinear spins. Okay, and to make a contrast between the twisted sample and the natural sample, we plot the two contributions for bilayer and four layer below here. So we can see that for 2 layer and 4 layer, we don't have the second contribution. Okay. Yeah. Okay, and I want to emphasize that the net magnetization naturally falls into the collinear spin part. That is also a consequence of the fit rather than a preset of the fit. Okay, so then in order to understand this data, we collaborated with Kai Sun at Michigan. So Kai provided us a spin Hamiltonian and then relaxed the spin Hamiltonian to find the ground state of the system. So the spin Hamiltonian is done in such a way. So we have bilayer plus bilayer. So then at the interface, we need to look for a location-dependent interlayer exchange coupling. So then Kai did this kind of twist and then look for the locations and then compare to this paper to identify what would be the interlayer stack, what would be the interlayer magnetic exchange coupling given this particular stacking geometry at the site. So then the spin Hamiltonian composed like sort of 4 parts. The first part is the interlayer ferromagnetic coupling with the easy access anisotropy. And then the second part is the interlayer anti-ferromagnetic coupling between first and second layer. And the third part is the interlayer anti-ferromagnetic coupling between third and fourth layer. And the last part is the modulated interlayer magnetic coupling between the second and third layer. Okay. And then the ground state shall be looked under this particular spin Hamiltonian. Okay. So when we look at it, we first notice that for this kind of intralayer ferromagnetic coupling, it would prefer a uniform spin alignment within the layer because we have strong easy access anisotropy there. But then when we look at this Moiré interlayer exchange coupling, it actually prefers a modulated spin textures there because we have both anti-ferro and ferro there. So then these two terms really will compete to each other and give the final result there. Okay. So then the competed result, okay, actually depends on the twist angle. Okay. For the very small twist angle at 0.1 degree, so we actually will have two layers that are modulated with a spin texture. And then you can see that when they are modulated, they actually modulated in the anti-ferromagnetic fashion. So then when we look at each regime or we look at everything together, the total magnetization along the Z direction is actually 0. Okay. And then when we look at the very large twist angle, we can see that they are actually homogeneous in every layer. So then for this particular situation, the total magnetization along the outer plane direction is also 0. What's interesting is in between, there is a twist angle regime. There is only one layer that is modulated. For this situation with only one layer that is modulated, we will actually have a non-zero magnetization along the outer plane direction. And that is seen in this island, because if you look at the island that is marked by the green, we will have upspin and then upspin and then downspin and then upspin. So that is against any natural state it would take. Okay. So then if we look into the field dependence, we sort of build up a picture trying to understand it, given this kind of magnetic ground state. So this is where we start with. As we increase the field, we were trying to expand the island with the polarization that is along the field direction. That's a slow increase between the below the critical field. Once above the critical field, the system want to flip in a way that majority of the spin is aligned along the field direction. That will make the switch between the second layer and the third layer, make the third layer inhomogeneous. But simultaneously, the island is pointing in the opposite direction of the field. So then when we crank up the field at this moment, the island should shrink gradually until disappear to form a uniform field. So that is sort of consistent with our trace here in the field dependent measurement. Okay. So then the answer to this competition is really twist angle dependence. So then the trend as a function of twist angle would be non-monotonic. So we will see a magnetization that was 0 to start with and then goes up and then goes back to 0. Okay, so then we check our twist angle dependence. These are just raw data. So the fitted twist angle dependence of the magnetization is plotted in this purple curve here. You can indeed see it goes up first and then goes back to 0 at large twist angle. Concurrently, we have this non-collinear spin weight we can plot out together, which is the slow changing component. That one has a similar trend as this magnetization trend. Okay. So I will skip here since we have limited time. So we look at the twist angle dependence of different parameters. We said for both the magnetization and the non-collinear spin weight, they all peak at 1.1 degree. So we also have our other parameters. So another parameter is a critical field for the spin flip transition. For that particular parameter, it dips at 1.1 degree, meaning that this kind of sort of like interaction between the two bilayers actually impacts the interlayer interaction within the bilayers. So its effect is more than just at the interface. Okay. And then the width of the critical field, however, peaks around 0.5 degree, which we don't understand. But then the slope of this gradual changing, it also peaks at 1.1 degree. So this kind of thing sort of points us that 1.1 degree perhaps is a spatial one. So then we look with more care here. So we do a temperature dependent measurement. The temperature dependent measurement, we do the same fitting as we did before. And then we're trying to see, as a function of temperature, the net magnetization onsets around 25 Kelvin, while the natural field layers, the layered anti-ferromagnetism onsets around 45 Kelvin. So the magnetization's onset temperature is actually nearly half suppressed. In addition to that, the non-collinear spin weight, it actually substantially decreased also around 25 Kelvin, rather than 45 Kelvin for the natural case. So similarly, we actually have a new temperature scale in this 1.1 twist sample. So then we want to ask whether it's because of the sample fabrication process somehow degraded the sample, so that make the onset temperature lower than expected. So we check with twisted double bilayer of 2 degrees, which is just slightly bigger than 1 degree. For the 2-degree case, we can clearly see the magnetization actually onsets at 45 Kelvin, as expected for the natural field layers critical temperature. So this tells us that the fabrication process didn't degrade the interaction in the sample. It is an intrinsic property of the 1.1 degree that had the lower temperature. So then we also would like to ask, since we see this so-called 25 Kelvin here, what about the 45 Kelvin? Do we see any signature about 45 Kelvin in this 1.1 twisted sample? The answer is yes. When we look at the critical field, it onsets at 45 Kelvin. When we look at the susceptibility of the system, which is a slope of our curve, it also diverges at 45 Kelvin. So the system actually have 2 temperature scales. One is 25 Kelvin, the other is 45 Kelvin. Our understanding is really because the competition between the interaction that brought the 2 energy scales into the system. Okay, so let me just quickly go through the last page with a puzzle. Okay, so for this twisted 1.1 degree, we thought it's very spatial, but then after that, we took a more careful look into the system. So we tried to plot the sweeping up and the sweeping down with different colors. So then for 1.1 degree and 2 degree, we can clearly see that the hysteresis loop is normal. So we have this counterclockwise hysteresis loop as people typically see. But then when we look at this 5-degree sample, you can see that the hysteresis loop, it actually goes to be clockwise, which is counterintuitive or unexpected. So then we add one more twist angle in between, which is 3.5 degree. When we look at the 3.5 degree, we actually see this kind of double loops with 0 magnetization at 0 field. Despite the strange shape, it actually is a good transition behavior between regular loop and the anti-hysteresis loop. So then we also repeated the data in the anti-hysteresis loop multiple times. So then we also did temperature dependence to see whether this kind of a regular or irregular loop maintains across the temperature range below the critical temperature. For the 2-degree one, so what we plot here is that the force color plot of sweeping up, then force color plot of sweeping down. And then this figure is constructed by sweeping down minus sweeping up. So if it's red, then it's a normal loop. If it's blue, it's an irregular loop. Okay, but then when we look at 1.1 degree, it's very strange. It's half normal, half not normal. In the previous study, we see that the magnetization onsets around 25 Kelvin. But in reality is that between 45 and 25, there is very weak magnetization we didn't notice before. And when we were able to notice them, they actually show this anti-hysteresis behavior. So this gets me to the end of the talk. So I hope to show you that we can do this twist to introduce new lattice into these twisted magnets, and this new lattice allows new magnetic states. But simultaneously, we also have a lot of puzzles in the system. Yeah, so let me just stop here and thank all the collaborators and thank you for your time.
In TMD bilayer, usually at small percentage, like a lot of things that you have seen one, there is a large atomic structure. So here, of course, you have 2 on 2. I wonder if you have any experimental evidence, say, from the PM, that they are
I think the answer is yes. The ability for them to see the new Moiré superlattice peak is one indication of the lattice actually reconstructed. Otherwise, they wouldn't see the new peaks.
But if there's a reconstruction, then when you try to model the behavior, that should impact.
Exactly. Yeah, so that's why when Kai calculate for the twist angle dependence for us, we don't expect magnetization up to 5 degree, but then experimentally we do see magnetization up to 5 degree. So that's perhaps arising from, we didn't account for the lattice relaxation there. Yes.
Can you just speak for any
Yes, we are currently collaborating with Chunhui Du's group, trying to use scanning NV magnetometry to look at this sample. Yes.
Okay. You expect the any variation, spatial variation in the single ion. So in the twisted system, you might expect local coordination of probing also spatially.
Yes, I think we do have. The reason is that when we do Raman spectroscopy measurement, we can see the acoustic branch of the magnon, which measures the anisotropy of the system. So for twisted sample versus natural sample, that acoustic branch's spin wave energy is different. So that perhaps is coming from the single site ion anisotropy is different, but then how it's modulated and whether we see the so-called Moiré magnon, we don't have result for now. Yeah, so for the TM samples, we have the thin HBN encapsulated on both sides of the actual sample, but we have to make the HBN quite thin so that the transmission electron microscopy can transmit it successfully. So, but simultaneously, because of this, we can not do atomic resolution transmission electron microscopy because now along the projection direction, you have too many atoms to be projected together. Yeah.
You mentioned the magnet. Is there any knowledge about magnets? Whether it's a particular angle that now you can smaller magnon gap.
For twisted one, I haven't seen like a full calculation of magnon dispersion into the system, primarily because perhaps the lattice relaxation is not considered. So then the whole spin Hamiltonian need to be revised. Yeah. So our result wise, yes, there's a twist angle dependence, but not clean enough because the magnon's energy is too low. So then when we do this measurement, when it shifts to the low side, we don't see it. Okay.
I'm curious, how does the gap change when you twist it?
Becomes smaller. So basically the magnon, the lower branch, the acoustic one, the frequency gets dropped when we twist it.